Hello and welcome to the online version of Math 1070. This is going to be a little weird for me because I'm basically sitting alone in a dark room talking to myself. But let's get started. The first thing we have to deal with in this class is we're going to need a review of everything in Chapter 2 that we learned in Math 1040, since this is a continuation of Math 1040, but we're going to be tested on the entirety of calculus, chapters 2 through 5. And this is going to be especially important to deal with in the scheme of things, since everything in calculus is a limit, which is suggested in section 2.1. 2.1. So we're going to deal with how to solve all these limits for chapter 2, and then the rest of calculus is basically finding new ways to avoid doing the limits, because limits can be pretty tedious. So in section 2.2, we give ourselves a more intuitive understanding of what a limit is. I like to add a little bit more math to it than the book does, so I'm going to start off with an extra definition. So first off, I'm going to define a sequence. A sequence, which is usually denoted a sub n in parentheses, is simply an enumerated list of values. So one of my favorite sequences we may recognize, well, let's just add a dot 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 there. So as you may have guessed, this sequence basically just gives us the digits of pi, which is, fun and all, but that doesn't really do anything for us. I can just find a new sequence, b sub n, where b sub 0 is equal to 1, b sub 2, whoops, I can count, I promise. B sub 1 is equal to 1/2, b sub 2 is equal to 1/4, b sub 3 is equal to 1/8, etc. And I can give a more general rule for these by saying b sub n is equal to, let's see, I had 1/2, I had 1/4, that's 2 squared, 1/8, 2 cubed, so this is 1 over 2 to the power of n. And if we think about it, this sequence, as n gets very large, the values for this sequence get very, very small. And we want an idea about that. So I'll add a new definition here. A sequence, we'll say it converges to a limit L if given any margin of error, which I denote with the Greek letter epsilon, there is a threshold, well, I should say threshold value, big N, such that for every n greater than big N, we have the absolute value of a sub n minus big L is less than epsilon. When I have an absolute value in an inequality like this, this is basically saying that L minus epsilon is less than a sub n is less than L plus epsilon. That's an interval, an open interval. So what this basically says is that my sequence is going to converge to some magic number L if, after a certain point, all of the terms of my sequence fall inside of this new interval here. And this is what we're going to be using to think about our limits. So in terms of b sub n here, we'll suppose we have a margin of error of 1 over 1,000. And I think that the limit of this sequence is going to be 0. So what I'm asking is there an index, big N, for which every sequence term of b sub n falls inside of negative 1 over 1,000 and positive 1 over 1,000, which is saying my L is equal to 0. I can cut my work in half a little bit, I suppose, because all of my b sub n terms, they're greater than 0. So in other words, is there a threshold, or I should say now, is there a point after which every term is less than 1 over 1,000? And basically that answer is yes. We'll have to find out what it is though. So first we'll say, is b sub n plus 1 the next term less than b sub n? Well, b sub n plus 1 is equal to 1 over 2 to the n plus 1, which by exponent properties is equal to 1 over 2 times 2 to the n, which is equal to 1 over 2, which is 1 over 2 to the n, but this guy right here is actually my b sub n, 1/2 of b sub n. So b sub n plus 1 is only half of b sub n, so this answer is yes. I didn't do anything special about these n's here, so I can just go ahead and assume that that's always true, which means my sequence is going to be shrinking. Every term is getting smaller, so I just need to find out the first time I'm smaller than 1 over 1,000. I only went up to 8 up here. Let's find out how far I need to go. I'll make myself a handy chart. N and b sub n. When I did 3, I got 1 over 8. So when I do 4, I'll have 1 over 16. Yes. 1 over 5 is 1 over 32. 1 over 6. 1 over 64. Oh dear. 7. I should have 1 over 128. Alright. 8th term is 1 over 256. Almost there. 9th term, 1 over 512. I bet you this next one will work. For the 10th term, I'll have 1 over 1024. This is less than 1 over 1000. Which means I have answered my question all the way back here. Is there a point after which every term is less than 1 over 1000? And we determined that yes, every term is shrinking. And this is the first term less than 1 over 1000. So for all n greater than 10, we can probably use 9, but let's just be safe. B sub n is less than 1 over 1000. This is all fascinating and fun, but we won't have to do it very often. What we really care about is having a sequence of numbers that converges to a particular spot. Because what I want to do with that is define a new limit. So a basic definition of a limit of a function f of x. So we say the limit of a function f of x as x approaches c is L if for any margin of error and sequence of x values, x sub n, which converges to c, there is a threshold big N such that the sequence of function evaluations f of x sub n minus L is less than epsilon. The sequence of function evaluations converges to L. And this is how we want to think about most of our limits. So if I were to find the limit as x goes to 2 of x minus 1, I would need to find the limit of the function evaluations for a sequence of x values which approaches 2. So I'll actually build myself two sequences. I'll do one from the left and one from the right. And since this has to be true for all of these sequences, these would better match. So we'll draw ourselves a nice little table. We'll have the x values and the function values. I can start off with 1.9, 1.99, 1.999, or forever until I get to, what does this look like? 2 minus 10 to the negative n. Here I'll get minus 1. So this is 0.9, 0.99, 0.999, dot, dot, dot. It looks like I get 1 minus 10 to the negative n in general. I'll do this again for the opposite side of 2. all of my x values, my y values. I'll have 2.1, 2.01, 2.001, etc. until I get to 2 plus 10 to the minus n. 1.1, 1.01, 1.001, and in general 1 plus 10 to the minus n. You notice this looks very similar to the previous work we did with these sequences, is all of my function values are going to be falling within an interval here between 1 plus 10 to the minus n and 1 minus 10 to the minus n. So we can declare this limit to be the function values are converging to 1. So we'll go ahead and say that this limit is equal to 1. So based on this existing definition that we have, we're able to prove various things about the limit to allow us to solve them a little more in general without the tedious legwork of, you know, plugging in 15 different values until we find a pattern. So we have section 2.3, limits using the limit laws. I could show each of these as true using the definition I just gave, but it's not very much fun and it doesn't really help us do anything with it, so I won't this time. Let's assume that the limit as x goes to a of f of x is equal to L, and the limit as x goes to a of g of x is equal to m. Then first up we've got sums. Exactly what we want to be true about sums is going to be true for limits. If I have the limit as x goes to a of f of x plus g of x, then this is going to be equal to the sum of the respective limits, or in short, L plus m. And of course, whatever is true for addition is also true for subtraction. So we've got that. If I have the limit of a constant multiple of a function, then this is equal to the constant multiple of the limit of that function, c times L. Similar thing happens for products of functions. If I have the limit as x goes to a of f of x times g of x, that will be equal to the limit of f of x, which is L, multiplied by the limit of g of x, which is m. And usually what's true for multiplication also works for division, but we need to worry about a problem. We'll see if we can spot it by the time I finish writing it. As x goes to a of f of x divided by g of x, this limit will be what we want, L divided by m, as long as m is not equal to 0. If the limit of g of x is 0 as x goes to a, then we're going to have a bit of a problem. But thankfully, we generally don't need to worry about that yet. We have other tools at our disposal. So if I needed to, for example, calculate the limit of a more complicated function, limit as x goes to 4 of f of x is equal to 5, limit as x goes to 4 of g of x is equal to 7, and the limit as x goes to 4 of h of x is equal to -3. Then I would be able to calculate the limit as x goes to 4 of 3 times f of x minus 2 times g of x, all divided by 1/2 of h of x times g of x. And I should try to handle this in parts. Let's see. First up, I suppose I should see that I have a division here. So according to the limit laws, I can use my fourth rule to say this is equal to the limit as x goes to 4 of 3 times f of x minus 2 times g of x. Apparently I wrote that a little funny up here. Let's fix that. Much better. And down here is all divided by the limit as x goes to 4 of 1/2 h of x times g of x. Now I can use a combination of the first two rules for the top half of this problem. So let's see. My limits will distribute across the addition and subtraction, but also constant multiples will come outside of limits. So the top half will look something like 3 times the limit as x goes to 4 of f of x minus 2 times the limit as x goes to 4 of g of x. Beautiful. Now on the bottom half, I have a constant multiple, but I also need to split up this multiplication. So I'll have 1/2 times the limit will distribute across the product. The limit as x goes to 4 of h of x times the limit as x goes to 4 of g of x. Now, technically, in order for me to do any of these steps, all of my limits at each stage of this process would have needed to exist. For example, in this first step here, I need the top half limit to exist, and I need the bottom half limit to exist, and I need to make sure that the bottom half limit is not equal to 0. But we kind of ignore those steps a little bit and just say, as long as my limits all exist as long as my number exists at the end of all this work here, I should be good to go, because I can work my way backwards through the arguments. Now what did I declare for f, g, and h? The limit of f is 5, the limit of g is 7, and the limit of h is -3. So this is equal to 3 times the limit as x goes to 4 of f of x, which is 5, minus 2 times 7, divided by 1/2 of -3 times 7. Which simplifies a little bit. I have 15 minus 14 divided by 1/2 times -21, or 1 over -21 divided by 2, or if I simplify that further, I have -2 over 21 as my final answer. We actually have some additional rules which are simply just consequences of having a continuous function. So let me define that. This is actually 2.4 stuff. F of x is continuous x equal to a if the limit as x goes to a of f of x is equal to f of a. In short, if the limit is equal to the function value, I have a continuous function. And continuous functions are extremely valuable for limits because a, if f of x is continuous and the limit as x goes to a of g of x is equal to L, then the limit as x goes to a of f of g of x is equal to f of L. This has the effect of allowing limits to pass through continuous functions. So in short, I'd be saying that this is equal to the limit as x goes to a of g of x inside of the function. My limit moved inside of my continuous function. Also b, if f of x is continuous, then the limit as x goes to a of f of x is just simply f of a. I can do direct substitution, and I don't have to worry about any of the limit law stuff. So some examples of continuous functions. We have our favorites, polynomials, root functions, etc., but also rational functions of polynomials on their domains, of course. If the function value doesn't exist, then I can't exactly set the limit equal to the function value because, well, yes. What am I missing? Sine of x, cosine of x, those are continuous everywhere. And exponential functions. Those are going to be our most common candidates. Well, maybe not candidates. Culprits, I suppose. So the last major topic we have out of section 2.3 is the squeeze theorem. And I'm going to present this in two parts. Part 1 is if f of x is less than g of x, or at least on an open interval containing x equal to a, then the limit as x goes to a of f of x will follow the same inequality. It will be less than or equal to the limit as x goes to a of g of x. And 2, the big part, if g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit as x goes to a, at least on an open interval containing a, like I said before, and the limit as x goes to a of g of x is equal to the limit as x goes to a of h of x, both equal to L, then the limit as x goes to a of f of x must also be equal to L, because it's essentially squeezed between the other two functions. So a popular example of one of these is something like, the limit as x goes to 0 of x times sine of 1 over x. This is a little difficult to look at because as x goes to 0, the 1 over x can do some pretty crazy stuff, and I don't know what the sine is going to do to that crazy stuff. But what I do know is that sine of anything is always between -1 and 1. So what I can do is say, hey, I've got x times -1 is less than or equal to x times sine of 1 over x, which is less than or equal to x times +1. And if I throw limits on all of these are going to follow suit by the first part of the squeeze theorem. -x is less than or equal to the limit as x goes to 0 of x times sine of 1 over x, less than or equal to the limit as x goes to 0 of x. Let me see here. This limit, that's easy to calculate because I can just plug in 0 and I'll get 0. So this is equal to 0. Same thing for the right-hand limit. But since those are both 0, that means this middle one must also be equal to 0 by the squeeze theorem. And I really want to think about the squeeze theorem anytime a part of my limit is bounded, or if I get stuck trying to do something else. Popular squeezes. We'll call it that. We could have sine of x, we can have cosine of x, and we can have arctangent. That's between pi over 2 and negative pi over 2. Arc cotangent, if you ever see that, that would do the same thing. Or any prompt that starts off saying, suppose f of x is greater than or smaller than something. That's a huge indicator that you're about to use a squeeze theorem. So let's take a look at some of the different types of problems I can see coming out of our limits. So for example, the limit as x goes to 5, x squared minus 6x plus 5 divided by x minus 5. The first thing you always want to try to do is plug in the number, but when we try to plug in 5, we get, let's see here, we get 25 minus 30 plus 5 over 5 minus 5. If I'm not mistaken, this is 0 over 0. This is an indeterminate form. And it basically says, do more work. Because we can't determine anything, hence the name, about what our limit is going to do until we actually try to do something. But what I do notice is since I got 0 divided by 0, that means 5 is a root of the top and it's a root of the bottom. So I'll try to factor these polynomials to see if I get a factor of x minus 5. On the top half, I get, let's see, x minus 1 times x minus 5. And the bottom is already all set, x minus 5. I can cancel these, and that has exactly canceled my problem. I get limit as x goes to 5 of x minus 1 left over, and since my problem has been canceled away there, I can just plug it in and I'll get, well, 4. Another favorite, I might have something like the limit as x goes to 4 of 1 minus the square root of x minus 3 all over x minus 4. Now what I notice here again is if I try to plug in 4, I'll have 1 minus the square root of 4 minus 3, that's 1, all over 4 minus 4, that's 0 over 0 again. But this time I don't have a polynomial, so I can't exactly factor this and try to cancel something. But I do have a square root, and I hate square roots, so I'm going to try to get rid of the square root. And the only way I can really get rid of a square root is to multiply and divide by the conjugate. It goes to 4, which is just a fancy word for changing the sign in front of the square root. So I'll have a 1 plus square root of x minus 3, whoops, minus 3, all over 1 plus the square root of x minus. And when I multiply this out, let's add some parentheses, because everybody likes parentheses. I'll get the limit as x goes to 4 of 1 minus parentheses x minus 3. All of this over, where did that 2 come from? That's silly, that's a 4. I have an x minus 4 times 1 plus the square root of x minus 3. I really don't want to deal with multiplying that out, so I won't. But when I simplify this, x goes to 4, 1 minus x minus 3. So that's minus x, 1 minus minus 3. That's plus 4. Silly. 1 plus x minus 3. There we go. I'd like to cancel this, but my signs are flipped. So I'll factor out an extra negative 1. Negative 1 times x minus 4 all over x minus 4. 1 plus the square root of x minus 3. Close. Now I can cancel these, and hence my problem has been canceled away now, because that was the problem. I'll have negative 1 over 1 plus the square root of x minus 3. What do I get out of that? If I plug in 4, I'll have negative 1 over 1 plus 1. Excellent. Negative 1/2. Algebraically, these are two of the simplest examples, but I could have more complicated situations arise, which require me to remember some higher factoring things. For example, if I have the limit as x goes to 1 of x to the 6th minus 1 over x to the 5th, whoops, minus 1. Now here, I mean, certainly I have x minus, if I plug in 1 to whatever power is just going to be 1, I'm going to get 0 over 0 over again. But factoring an x minus 1 out of these can be kind of hard. I could try a polynomial long division, but nobody wants to do that. But I do have more general factoring rules at my disposal. For the top half, I'll say that x to the 6th is equal to x cubed squared. So this top half will be x cubed plus 1 times x cubed minus 1. I'll leave the bottom alone for now, because it's scary. We have factoring rules for the sums and for the differences of cubes. So first up, we have, this works like x plus 1 times x squared plus 1 times x minus a 1 squared. And similarly over here, we'll have an x minus 1 x squared plus 1 times x minus, plus a 1 squared. Lovely. X to the 5th minus 1. This factor rule I used for the cubes here actually generalizes to higher powers, and I'll write out what it looks like. Squared plus x minus 1, x minus 1 times x squared plus x plus 1. Down here I'll have x minus 1 multiplied by x to the 4th plus x cubed times 1 plus x squared times 1 squared plus x times 1 cubed plus 1 to the 4th. Which is nice and all, but what I care most about is now I have these x minus 1s and I can cancel them. Alright. Since those are gone, I can go ahead and evaluate this limit. I have x plus 1, x squared plus x minus 1, x squared plus x plus 1, all over x to the fourth plus x cubed plus x squared plus x plus 1. This turns out to look like I'll have 2 times 1 plus 1 minus 1. 1 times 3 all over 1 plus 1 plus 1 plus 1. I lost count. 1 plus 1 plus 1 plus 1 plus 1. Whatever. 5. Which is equal to 6 over 5. Let me check that answer with my knowledge of the ages, and that is correct. So that concludes this first video, and I hope we're all looking forward to the next installment of me talking to myself in a dark room.